All right. Good afternoon, everyone. I hope everybody's enjoying their lunch today. Thank you for sharing it with us today. We're going to talk about home performance and why it's so important and why it's not that hard uh, and why it's so important for electrification. So some of the things you're going to learn today, a couple of the unintended consequences of unplanned heat pump swaps. It's always good to plan this stuff out. We're going to explain to you why load calculations are so important, understand why standard BTU to kilowatt conversion doesn't necessarily mean perfect right sizing, and calculate how many BTUs are lost to the attic with uninsulated ductwork. So pretty cool slide deck we've got going here today. We got pretty much all of this out of the way. We're going to show you some project examples today, or at least one good project example. We kind of have a lot of slides. And then we'll do the class survey, close, and wrap up and take care of any questions at the end today. Alex, who's usually on these calls with me, is home enjoying his new 7-day-old daughter. I think he slept a total of 2.5 hours in the last week. We all know, a lot of us know what that's about. This is the last in our series of 6. It's kind of a melancholy end to this group. We're hoping to provide more of these in the future for PG&E. And today, why and how of home performance in electrification. As always, hashtag Electrify Efficiently is our hashtag. You'll see that about on different social medias. And for us, it's not about electrifying everything. I don't look at the whole world through a how I could plug this in lens. It's how we can do this for the best efficiency and the best outcomes. And we talk about building electrification. Single family residential is what we concentrate on. We do HVAC, water heating, and some other services, all heat pump stuff. Overcoming the barriers that you might think are out there. And we always take approaches that optimize comfort, efficiency, resilience, and low operational cost. And I think everybody's going to benefit from this, but especially the contractors and industry people today. So let's start with the basics. Like, what is home performance? So home performance is a description of all aspects of how the house works together as a single system. And we talk about this as the house as a system approach, the whole house approach, or like the building performance vision of the building. And really, it's a science-backed approach that's based on the premise that houses should be safe, healthy, comfortable, durable, and efficient. And the one that we always add to our systems is quiet. If my systems aren't quiet enough for you not to be able to hear them, a good heat pump system should fade into the background of your life. You shouldn't have to worry about the thermostat. You shouldn't have to worry about turning the TV up. All of that stuff can be a thing of the past if you do this right. We're going to think beyond the box a little bit today. We have our special motto of the day. The best outcomes for heat pumps come when multiple elements of the home are considered. We're going to get into that. But let's go into the basics of home performance first. So a lot of people know what the basic physics second law of thermodynamics is. I know this law of thermodynamics really well. I like to consider myself a lawyer in the law of thermodynamics. But I don't know what the first law of thermodynamics is. If anybody could fill me in on that. Energy flows naturally from high to low concentration. So if you have pressure differentials, pressures are always going to go from high to low. Heat is always going to flow from warm to cold. Moisture always flows from more to less. And energy in equals energy out. And when it comes to building leakage, one CFM leaking out somewhere is another CFM being pulled in somewhere. And I think everybody on the call knows CFM is cubic feet per minute. And when we talk about air, it's about a basketball sized amount of air. So we often communicate this as how many basketballs of air are going in and out of your building envelope. There's 3 critical elements of a good building enclosure, or any building enclosure. Sometimes they're not good because these elements aren't treated properly. But you have your air barrier, your pressure boundary, and your thermal boundary. And so the air barrier is the actual inside of your room. If you guys look around in your room and you probably see some drywall or some lath and plaster and your doors and your windows, anything that's keeping air from moving inside and out of that particular room you're in or that particular structure you're in is the air barrier. What we want the air barrier to do is it needs to be impermeable to airflow as much as possible. It should be continuous over the entire building enclosure. In other words, like when you see the wall and the ceiling match, there should be no area where there's a crack at the top where air can get through. It should be able to withstand the forces that may act on them, like wind and other bad stuff. It should be put into a place that's durable over the expected lifetime of the building. And anybody that's living in an old city house understands, like that lath and plaster is pretty darn durable until you try to drill a hole in it or cut a hole in it. And it also defines the location of the pressure boundary. So if you're in a house right now or in a building that has a crawl space and it also has an attic, those are the pressure boundaries. The outside wall is the pressure boundaries separating you from the outside forces. What we want to do is make sure that our internal air barrier has a good pressure boundary around it, and that's where it comes into air sealing. A lot of times we'll see leakage into an attic space where there's an actual break in the pressure boundary and the air barrier and the thermal barrier all at the same time. So pressure boundary. That's the point at which inside and outside air are separated, stopping air and vapor penetration into the building. If you take a look at this picture here, this is not only a giant air leak, this is a pressure boundary problem because it's breaking the differential of pressure from under the house to in the house. So if a house was pressurized and in a positive pressure, the air is going to leak out this way. If the house is in a negative pressure, it's going to pull in this way. So it's important that these things are sealed up as good as possible. And the pressure boundary is going to be that spot where the sealing should be done. It should also separate all conditioned spaces. It should separate your garage from your conditioned space. It's also important if you have combustion appliances in a certain pressure boundary. And the thermal and pressure boundaries should be aligned. Thermal boundaries. Now, when you have an air barrier, you have the drywall or you have the ceiling. When you have insulation connected directly to the back of the drywall or the lath and plaster, whatever your air barrier is made of, as soon as you apply insulation to that, that creates the thermal boundary. If you have drywall here and insulation here and it's not making contact there, you don't have a thermal barrier. You just have a place where air and heat is going to escape between the insulation. It's really important to look at that way. So it's the plane of the building surrounding the space that is intentionally heated or cooled. This is where the insulation should be located. Created by the presence of insulation in complete and continuous contact with the air barrier. This is really important, and then we have a slide coming up to demonstrate how this breaks in a lot of homes. It restricts or slows the heat transmission through the building enclosure. It cannot exist without an air barrier. If this happens a lot in attic spaces, they put a bat of insulation over an interstitial wall cavity. There is no air barrier between that. That is not a thermal boundary or a thermal barrier. There has to be an air block and insulation on top or on the side of it in order for it to become an actual thermal boundary. It's a necessity for an energy efficient building. Buildings that do not have an effective thermal boundary, we need to make adjustments in that when possible, and we need to make the right adjustments that make the most sense for the customer at the time as well. Here's an example of two homes, and one has a vaulted ceiling and one has an attic space. And our thermal boundary can exist in two different areas here. If we have a vaulted ceiling or a ceiling where we can actually see the top where it follows the roof line up, that's where the thermal boundary needs to go. That's where your insulation needs to go. aligned with your air barrier, so it creates that difference. And this we would have a thermal boundary that separates a pressure boundary, because the pressure in your attic is going to be different than the pressure in your house. So thermal boundaries can exist in different spaces depending on where that air barrier is installed. Air leakage. This is a huge problem. And when you have a leaky house that has pressure differentials in it, and there is ways for that air to get into the building, this really causes a huge problem. And just to explain this picture a bit, we don't often get to see what's behind the walls. We do have thermal imaging that we can do, so we can kind of see what the result of something like this is. But it's rare when we get the opportunity to actually look in here. And this was a job I did probably 10 years ago. And they were doing a bathroom remodel. And they bought this house, and the ductwork was really bad. And there was probably half of the houses in this neighborhood in Napa were like this. And what you see here is the telltale sign is this roof flashing. So there's a roof flashing going on behind here. And so behind here was an outer knee wall. So this is this is like the outer siding on the other side of this paper. And then this under here was the attic space that the flashing was protecting from leaking into. So what this house, all the way across the front of the house, it had a shorter roof line, and that shorter roof line was an attic space that got very hot, and it was interconnected with all of these walls. So when we found this, what we did is we ended up sealing all of these, but we noticed also that if we looked under here and looked this way, we could also see into the attic. So this attic air was leaking inside the walls and between the floors. Now, there's not a lot of opportunity. You're not going to go rip all your drywall out and go seal all this stuff, but we need to be aware of it. All these things can be fixed. The way this could have been fixed from the other side is there was a crawl space. This kind of went over the garage. There was a space where these cavities for the floor joists could have been sealed from the other side. We ended up sealing them from this side, and then we sealed up all of this area here so that the attic transmission wasn't coming inside the walls anymore. But air leakage is really, really, really an important thing to fix whenever we get the opportunity to. And once again, we can't tear our houses down to fix this stuff, but when we run across these problems, we can certainly fix them in real time. Infiltration and exfiltration. So air leaks out of houses and air leaks into houses depending on the driving force that's happening. And sometimes the driving force can just be leaky ductwork. This is why it's really, really important for us to identify ductwork problems in the house and things like return air cavities that are using floor joists as the return. Those can often cause a positive pressure in the house because air is coming into the system from other places than the return air grill. And when that happens, when the system is pulling through the return air grill and it's also pulling from other parts of the house, that means it's pushing more air back into the house than it's pulling out of the envelope. And that causes this thing called infiltration, which is basically a pressurization of the house. The infiltration, what it does is it drives your conditioned air out. So all that money that you've spent on keeping your house, trying to cool your house, and your system is constantly blowing that conditioned air through all the cracks. The other one is with ductwork is when you have a leaky supply side ductwork. So say the ductwork in your attic has big gaps or holes or whatever. And so our system is pulling air from the house, blowing it up into a leaky duct system. That means the air is leaking out of the supply side, which means we're pulling more air through the system than we're putting back into the house. That causes infiltration. And infiltration is basically the opposite. So now we're pulling the unconditioned air from outside in through all the cracks, and it's still fighting our system. So we hear this all the time, that houses have to breathe, and there's a certain truth to that. But our system that is designed to move air through the system, our duct system in our house, needs to be sealed tightly on both sides so that we're not creating that driving force during the operation of conditioning our homes, that we're not causing that driving force that's either pushing out your conditioned air or pulling in unconditioned air. And the easy way to remember that is supply leaks suck and return air leaks blow. So of all the research that we've done and all of the information that we've gotten through our compatriots out there that are looking at a lot of houses and doing blower door tests and things like we do, we found that air leakage in the building can represent as small as 5% or up to 40% of the space conditioning costs. So if you're putting in a new heat pump, and generally heat pumps are smaller, and we'll get into that in a minute, but when you're putting in a new heat pump and we're now conditioning the house with less heat than we had before, and we've got a ton of air leaks, and those air leaks are causing 40% of our space conditioning cost, that can drive the efficiency of the heat pump way down, which means it's going to drive the cost of operating it way up. It's also going to, in turn, cause a lot of comfort issues in the house. Here's a picture of some air leakage we found. This is, if you have a house, this is in a lot of older craftsman homes. And craftsman homes, they have these built-in, beautiful built-in china cabinets and bookshelves and dressers and stuff. And it was really kind of a neat thing to do back in the old days. And they're beautiful to look at, but they're horrendous for building performance. And what we see here is standing in the attic space, looking down at the top of one of these built-in china cabinets. And so what you see here is all of this uninsulated wall cavity here, all of this is causing a break in the pressure boundary. There is no thermal boundary, and the air barrier is broken because these china cabinets often are kind of open in the back behind the drawers and whatnot. So it's really important to deal with these at the time of dealing with it. And you can tell they had a new roof installed at some point because roofers don't care and they just drop all the stuff in the attic. But you can also see in this house that they had insulation installed, but the insulator didn't have a good enough understanding of what this was. So they paid a lot of money to have insulation installed, and they still have these massive problems in the house. And these are pretty easy to fix. We do it with foam board, and we just cut foam board out, and this is really part of the funnest job that we have. We cut the foam board out to fit the space, we jam it in there, and then we get to use the foam gun to seal all around it. So we took this big, giant, energy-sucking cavity, and we were able to fix it in about a half an hour with probably $20 worth of materials. This particular house, this customer is going to save a bundle just for that part. We'll show you more pictures of that in a few. When electrifying, we also, because once again, we're using less capacity to heat our homes than we did with big, giant, inefficient furnaces, we need to take care of things like sealing the combustion vents. If we have a furnace that's in a closet like this house, this is inside the building envelope. You can see they got a little bit of weather stripping around the door, probably because the cold air was coming through there, and some homeowner did that. But in order for this furnace to run in this closet space, there's open spaces that go underneath the house, and there's a pathway usually to the attic space. And that's so you can have a high and low combustion air, because furnaces need air to burn, right? They use the air to burn and the exhaust. And when one of these systems with a fan here that exhausts this out, these things can pull like 50 cubic feet of air through every minute, some of them. So by the time it's used that air for combustion and exhaust, it's moving a lot of air through there. So when we come back with a heat pump that does not need combustion air, we need to make sure that those are sealed in the attic spaces. The other thing is we need to make sure our return air sizes are big enough. And then this is actually looking past here with a flashlight, all these open wall bays inside of this return. So this house had a massive overpressurization problem, because when this big giant monster furnace was running with all of its waste heat, it was pulling air from inside all of these cavities. The pathway for this, I don't know if you can kind of see this outline here, there was also the access to the underfloor was inside the return air cavity, which was terrifically difficult to get to. And the return air pathway was coming here. The furnace was actually over on a platform here. So it was pulling air through all these wall cavities. It was pulling some air from directly underneath the house before it got to pull the air from inside the house. So that causes a massive overpressurization of the house, which means they pay a lot of money to run this furnace, and a lot of the heat goes right out all of the cracks. We find a lot of insulation problems with houses that had gas systems because really nobody thinks about this. If you've got a big giant furnace in your house and it turns on because it's completely oversized and it turns on and it warms the house up, a lot of these problems never get discovered because you call a guy to come out and do an AC tune or a heating tune-up, and he never leaves the front of the furnace. He like cleans the whatever and does the whatever, but they never go up to actually look and see what the efficiency of the actual house was. And for us to install, if we were going to take out this furnace and just pop a new heat pump in there, and we had all of these insulation problems and all of this kind of really pretty poor ductwork, we would just be using a lot of the capacity of our heat pump just to keep these areas neutral. So it's really important that we apply some of this building science with these heat pump installs, because we're dealing with a lot less capacity here. Here's an example of home performance done wrong. And so what you see here in this picture is I've got the little isinglass here kind of focusing on the upper area, and you can see a little of it here. But this customer, in an effort to try to reduce the temperature of their upstairs attic space, it wasn't attic space, it was rooms built out in the attic with knee walls. When I came to this job, there was no insulation here, and they had insulated under the roof as the kind of solution to reduce the temperature in the attic space. But what they didn't do is they didn't follow this air seal and foam insulation job. Should have also been on this wall. And when you're sealing the inside of the attic space, because what you're really doing is moving that thermal barrier up to the underside of the roof, you can't just leave giant vents in there. This was still an attic, and this foam underneath the roof was just a waste of money. So we came in and actually insulated the knee walls with R13 insulation, and then we wrapped it with a nice R8, or might have even been an R16, I can't remember. This is called an FSK insulation, and it's got a second air barrier. So when we put this insulation in and kind of nailed it to the studs below and got this nice impervious area here, you can see that it was even taped on the seam. This created a double-sided air barrier on this wall, and we actually applied the thermal boundary to the drywall. We applied the insulation to the drywall and created the thermal boundary. They were trying to treat the underside of the ceiling as the thermal boundary, but this was still an attic because they left the ventilation. R value as it pertains to insulation. So R value is the measurement of the resistance of the conductive flow of heat. The measured R value is going to vary depending on what type of material you use. If you use blown foam, we can get a pretty good R value out of that for the amount of distance we need to fill. And with blown foam, we also get air sealing kind of in the same thing. But like looking at the slide before, blown foam doesn't work if it's not applied properly. And we would hope if we called an insulation contractor and we had them do that they would understand the basic principles of building science. But so far in a few of these pictures, you can tell they don't. The R is the resistance to energy and heat flow, and you can communicate this as, if I have R19 in the walls, these are all 2x6 walls in this particular picture. If I have R19 in the walls, that means I need at least a 19-degree temperature differential across this wall before any energy is going to move through. Once I've achieved a temperature difference across that assembly that exceeds the R value, some energy is going to come through back and forth. That's why when we do attic spaces, we're typically installing insulation at about 17 to 20 inches to achieve a R50, which means we're actually giving you 50 degrees protection from the attic space to the ceiling. So if you have a 75-degree house, you're trying to cool it off in the summer, and the attic is 125 degrees, we're not moving any energy through there. It's only after the attic achieves a temperature differential of over 50 or over 125 at 75 degrees in the house, are we going to start radiating heat down through the ceiling. So the more insulation, the better. Insulation is cheap. Put in as much as you can fit and do it right. It's also important that this stuff gets installed right, because poorly installed insulation in the walls are responsible for a lot of problems. And once the drywall is installed, there's really not a chance to go in there and fix it. If you have really bad insulation in these walls, you can't like drill a hole in the drywall and try to fill this with loose fill insulation. It's not going to work. It's not going to go in. So you only have one chance to do this sort of thing right. And so what we say is insulation has to make contact on all 6 sides: top, bottom, sides, back, and front. It needs to be contacting all of those different cavity areas in order to be super efficient. Otherwise, air can move through and get between those surfaces, and it cancels out that thermal boundary. So calculating duct gain, this is a big deal. It's something we look at on all jobs. We typically put systems in that are much smaller because we go through this process to reduce the capacity size of the house. And so if you have a house, and a lot of these in California were built from the 60s and single-story houses until recently. Now the systems are mostly going in the attic. But anytime that there's a furnace in a closet or in a garage and the ductwork goes into the attic, we can use this formula to find out how much improvement we can make. And so we use this, and what we're looking at here is our example is always a 1,500 square foot house. Most of the time ductwork is, if we see ductwork in the attic space that's metal and it's wrapped with yellow insulation, that's usually an insulation less than R4. It's usually R3 or so. Asbestos around R3 or so. Ductboard a little bit better than that. But we can take what our efficiency of our duct system is. We go up there, we see flex duct in the attic. We can see where it says R4.2. We can do this math. So we're going to use an example of a 1,500 square foot house. So this is a BPI, Building Performance Institute standard way of looking at this. And so we take the square footage of the home times 0.4. And why we're doing that is because it's shown that duct systems that are inside the attic space, if we took them all out of the attic and we measured the internal surface area of the ductwork, it equals about 40% of the square footage of the house. So if we have a 1,000 square foot house, it's typical that we will find about 400 square feet of internal duct surface area. So that's why we use the 0.4 here. Then you're going to take the temperature difference of the air going through the duct, and we use a very conservative number of 125, but the attic temperature versus the cold air temperature traveling through the ductwork. So in this example, we're going to use a 125 degree duct. We're running our air conditioner at 55 degrees, because generally a properly working air conditioner at 75 degrees in the house is going to put around 55 to 58 degree air out the other side. So for the sake of the math problem, we're going to use 55 degree temperature differential. And once again, that's the temperature of the attic versus the temperature of the air going through the ductwork. So this is how we do the math. This particular one here, I don't know why my numbers don't match, but we're looking at R3 insulation because that's what that yellow fuzz is on metal ductwork. So we take R3 ducts, we take 1,500 square foot times 0.4. That's going to give us our total duct surface area, and then we're going to times that by the temperature difference of the air traveling through the duct when the air conditioner's on, and a conservative temperature of the attic space. I always use this number, and then people go, no, it's like 140 in the attic. It is, but this is a number that's easy to calculate. So we do that math, and it's 42,000 over 3. We divide that into the R value of the ductwork, and we find that our system is using 14,000 BTUs, 1.2 tons of capacity, just keeping those ducts neutral under these conditions. So anytime it's warmer in the attic, this number is going to be bigger. If you're trying to push colder air through the duct, this number is going to be bigger. If we bury that ductwork in insulation, so we lay the ductwork down low, we put some nice new ductwork in there, we lay it down low, and then we cover it with R50 insulation, and we get most of the ductwork covered, so there's an average coverage, we can say that that ductwork now has an R30 insulation on it instead of R3. That drops our reduction of loss down to 1,400 BTUs. So we've now gone from 14,000 to 1,400, and all we've done is put in some new ductwork and buried it with insulation. And that's over 1 ton of cooling capacity. So 1 ton of cooling capacity is a big deal, because if you have this 1,500 square foot home, and you're going to, and it has a 3-ton air conditioner in it, which is pretty typical for that size system. That means we can now put in a 2-ton air conditioner and bury the ductwork and get better performance, right? My smaller system is going to use less energy. And so we've just through this small improvement in the house gained 30% of the capacity from our system that is being wasted to the attic in the summer and brought it back into the equation. So now there's a secondary benefit for this. When we blow this R50 insulation into the attic, we're actually creating a thermal barrier between the hot attic temperature and the house itself. So the way we figure that out is we take the U factor, and we're not going to go into how to calculate U factor, but that's the way this math on this one works. So we're doing ceiling heat loss or gain calculation. It's U factor times square footage of the house by temperature difference. And now we're looking at the temperature difference between the attic and the house and the square footage of the house. So the same house, 1,500 square foot house with a ceiling, ducts are in the attic. The attic is 125. We're trying to cool our house to 75 degrees. With R10 insulation, we use that number because it's nice and easy to figure out. And we go in a lot of attics, and that's about what they got, right? If you can see the top of the rafters on a lot of this insulation that's up there, especially the blown in yellow or pink stuff, you're really at R10, R13 maybe. But we take R10 as the factor because it's easy to understand. We times that by the square footage and then by the temperature difference. And we get that, it's 0.1. And what we've done here is, if anybody doesn't know, this is where we've actually changed R value into U factor. Because you take the R value, divide it into the U factor, and that gives you, or you divide it by 1, and that gives you the U factor. Times 1,500 times 50, and that means 7,500 BTUs. With R10 insulation, my attic at 125 and a 75-degree house is pushing 7,500 BTUs every hour into the house. So with that same insulation job that we're doing to bury our ductwork, R49, I think I could do R50 on this to be easier to understand. But R49, so we take 1 over R49 times 1,500, we do all the same thing, same calculation here. And now with R49 in the attic, we're only pushing 1,500 BTUs through the ceiling every hour. So that's a net gain, another net gain. We're saving 6,000 BTUs per hour. And so that is another half a ton of cooling capacity. So this works the same way in heat when we're protecting our warm air that's in the ductwork from the cold attic. So we've just gained another half ton of cooling. So what we've done here in this 1,500 square foot house with a 3-ton heating or air conditioning system, and most of the time, if you have a 3-ton air conditioning system, it's going to be connected to like a bigger furnace. So we have to figure out how we can take that 3-ton system and make it more efficient, because if we take out a big furnace that's connected to a 3-ton, we'll talk about that in a minute, but and then we try to put a heat pump in that's 3-ton. And so now we have a 36,000 BTU heating system. It's really important that we do these steps. Otherwise, we're heating with a lot less capacity. So if we're looking at a high performance enclosure specification, it's kind of a standardization. We want to have our enclosure leakage. And if anybody knows what a blower door is, it's this cool little contraption that we can set up in your door. and it's got a fan on it, and it's got a electronic device, and we turn that fan on, it pulls a negative pressure in your home, it compares the pressure to outside, and the little electronic manometer will tell you how much leakage you have. And then we actually divide that by the square footage. So if you have a 1,500 square foot house, a super tight, what we call high performance enclosure would be 0.5 CFM50 per square foot. So that 1,500 square foot house at a really, really tight house is going to be 750 CFM50. Most of the time we see houses that leak about 1.5 or 2. So for 1,500 square foot house that's leaky, we often see those at 3,000 CFM50. So it's twice, really 4 times what it should be. And then it's not hard for us to seal the big air leaks in the house and take care of those interstitial wall cavities and get the house down to 1 CFM50 per square foot. So if we can get the house down to 1 CFM50 per square foot, that's really what we would call a pretty good enclosure. So in a high performance enclosure, we should also have all attic bypasses and unsealed interstitial wall cavities fixed. You can identify these with an IR camera. Not everybody has an IR camera, but when we do blower door testing, we want to go out to a house that they're heating in the morning, so the attic is cold. So when we start up the blower door, we can actually see the air leaking inside the walls with a thermal camera. With a high performance enclosure, you can't find any of those. And then you also have to have good window performance, and that needs to be verified and accounted for in the sizing calculations. We'll talk more about that in a couple of minutes. So a high performance electric home with a ducted mini split. We're looking for something that's going to have a cooling sear and ear around 20 and 12. I think in previous shows we have talked more about the SEER rating, and before this year with SEER 2, how it was a national rating, and it's really a number that's based on a very low temperature. And since in California we don't turn our air conditioners on at 84 degrees, the SEER rating before this year was never really something that was really applicable to California. So we've always looked at this thing called the EER rating, and that's really how efficient that unit works when it's 95 degrees outside. We want a heating HSPF of about 12 if we can get it. Maximum heating capacity, we don't want one of our systems to have more than 10 BTUs per square foot. Sometimes we have to make the equipment fit. We want our cooling capacity is good. If we can get it up to this 1,200 square feet per ton. Now there's these things that are used by contractors out there. I was just talking to a customer this morning that had a 1,000 square foot home, and they've gotten bids for 3-ton air conditioners, 36,000 BTUs for 1,000 square feet. So they were really looking at, I can't even do the math right now, but they were looking at about 350 square feet per ton. 1,200 square feet per ton is doable. We do it all the time, and it doesn't take that much extra work. That is pushing it for what we do though. So ducts and air handler location. This is if you were going to have the highest performance system, you would want that to be 100% in the conditioned space. In most houses, you can't do that, but if you're putting one into a furnace closet and you're sealing the combustion air and you seal the furnace closet really well, that system, at least the air handler, has come into the conditioned space. It would be my preference on every house if we could find a place where I could run all the ducts inside the conditioned space, but it's not necessarily applicable. We want our duct insulation on our systems to be at least R8. If we have R4.2 in a lot of older houses now, and I hear people ask me all the time when they call and consult with us, it's like, we want to figure a way to do this with the existing duct system. And I said, if you're trying to do this with existing duct systems, I'm not saying you can never do it with them, but you're looking at this whole thing the wrong way. Because if we have really bad, inefficient ductwork, we have to put a bigger system in, which is going to use more energy, and it's going to be less comfortable. So we always want to put in R8. We want to keep our supply grill delivery velocity And this is a good one if you want to call a contractor and weed out people that don't understand building science and just ask them what their supply grill delivery velocity should be. And most of them are going to go, what's that? But this is how many feet per minute of air go through the supply system. And we want between 500 and 700. 700 is a little on the high side. That can cause a little noise on the grills sometimes. That's going to give us good airflow mixing characteristics. So the faster we can blow the air out of the vent in a single direction, the more entrainment it's going to do behind it, and it's going to mix the air in the room through just a fluid mixture like a stream. The return air grill sizes on, once again, a high performance electric system should be 600 square foot per ton. And so that's 20 by 30 return air grill on a 1 ton system. Now, I will tell you, look, when we install systems, we go up to 18,000 BTUs on a 600 square inch grill. And that's going to be a 20 by 30 return air grill. But it's also, opening. It's also important to consider the grill. Like the grills that are in most houses are very restrictive. Most of them have about a 30 to 40% face drop. Some of the older ones with really narrow vents are up to a 60% face drop. In other words, they're taking that space and they're reducing the amount of air you can move through it because of the grill itself. So it's really important on heat pump jobs that we put in a very high flowing grill, whether it be a bar type or a cube core or something like that. So we're moving as much air through that return as we can. When we move the air through a larger return, we're lowering the face velocity on the return, which makes for super quiet systems. And it also makes for the unit not to have to pull the air through as hard. And so there's a thing in the industry called a sound loop. And it's basically a way for people to make systems quieter by adding another 20 feet of duct in the attic space. And all they're doing is really reducing the ability to move air through to make it quieter, when what they should have done is provided the right size opening and the right size duct, and you just don't hear it anyway. Duct leakage, we want to make sure we're lower than 5 CFM25 to the outside. Now, this can really be a big lift on some of the systems we install, because oftentimes we install 12,000 and 18,000 BTU systems, and a 12,000 BTU system is only capable of 400 CFM, and 5% of 400 CFM is 20 CFM of leakage. That's a really, really, really tight duct system. Return temperatures, all the room temperatures should be the same within, oh, we got a typo there, not 30 degrees. If I have 30-degree differential in the room temperatures, I'm expecting my customers to call me. It's actually 3 degrees. I didn't look at that one close enough, sorry. Total static pressure, we want less than 15 if we can get it with clean filters. This is not always doable either, but what we're talking about here is a high performance electric home with a ducted mini split. This is the best results we're always shooting for. And if we shoot for these, we're going to get somewhere close. High performance unitary. So unitary, if you've been on some of these shows before, unitary is the big American made stuff, the big stuff that's really loud that goes in your backyard, that the brochure says as low as 72 decibels, those big monsters. A lot of the characteristics are the same as the ducted mini splits. We're looking for cooling efficiencies of at least 16 and 12 on these type of systems, and then measured sensible EER. With unitary single stage equipment, there is a way to do EER verification, what we call delivered EER, and that can tell you exactly what your delivered efficiency is in the house. That's harder to do with the inverter systems that we use, because the inverter systems are constantly adjusting to the exact need of the house. Cooling capacity, we still want that to be 1,200 CFM or 1,200 square feet per ton. In California, we have really dry climate. So we want to move our air across the cooling coil as fast as we can. So sometimes it's beneficial to have a little bit more air speed than we do compressing capacity, so that we can move the air across the coil really quickly, and then the coil doesn't get as cold, so it doesn't remove as much moisture. So you get more sensible cooling than you do latent cooling, which is basically moisture removal. the faster you can get that thing to spin on a unitary system and the more airflow you get through that system, the better. Return air grill size, we still want 600 square inches per ton. 70% of runtime at design temperature. So to check the sizing on one of these systems, if you have design temperature, if you're living in an area where your design temperature is 96 degrees, that unit should run like 70% of the day. Standby watts, you don't want a system that has more than 10 watts of standby watts, and a lot of these systems do. I notice I have like an air cleaning light on my system in my house, and I notice that thing takes like 25 watts all the time. So that's just energy you're using for no reason. And then return air grill size, and then total static pressure. We want the static pressure to be as low as possible. We have equipment out there now that can do more static pressure and blow, but that doesn't mean we want to stick it on old bad ductwork. That's not an excuse to do poor work. It's just a benefit that system can overcome some resistance in the duct system and push the air a little more efficiently through the system. And the reason they can do that with a lot of heat pumps is we're only pushing the air through a coil. We're not also trying to push it through a heat exchanger and a diverter plate. So the unintended consequences of box swaps, and what we call a box swap is when you call a company out to do a tune-up on your system, and they say, "Oh, Mrs. Jones, look, you've got this problem with your system. It's 20 years old. Look, it's got a little rust and a little dirt on it, and this has lived longer than most systems like it, and we just need to put a new system in for you." And when consumers buy under those conditions, oftentimes they get what we call a box swap, which is the exact same thing being put in that's taking out, only new and shiny. And so there's not really much efficiency to be gained by doing that, because we're not doing any kind of additional sizing. And typically what you're going to get is systems that are 40 to 60 BTUs per square foot. Remember on that slide we showed you before, 10 BTUs per square foot is high performance. Most houses with a 1,500 square foot, most 1,500 square foot houses with air conditioning or without have at least a 60,000 BTU furnace. And if you do the math really quickly on 60,000 BTUs into 1,500, that's a lot of BTUs per square foot. So 60, no, 40. Anyway. Waste heat, because furnaces have all this capacity, they create this waste heat. And so all this waste heat that you're paying for is just getting lost in all of these building assemblies, like the attic space and the interstitial wall cavities and the bad ductwork and the leaky returns. All that's just getting lost, but you don't know it because you have all of this heat coming into the house and you're warm and toasty. And then you get your utility bill and go, wow, why is my gas bill $600? And it's because you're just comfortable in your house, but your heat is leaking out everywhere. So imagine just for a moment that we didn't do any work on the house in that case, and we put a system in that's half that size, and there was no more waste heat, but you still had all the waste. What that just means that you're going to deliver uncomfort. So you notice that that your furnace, if you have a furnace in your house, forced air furnace now, on the milder days, if it has really short cycles, and I hear this all the time from customers when I say, "How's your furnace work?" And they go, "Oh, it works great. It heats my house up in 5 minutes." And that is not a good house. That house has way too much capacity, because even when it's mild outside, your furnace should run at least a 20-minute cycle every time. Otherwise, it never gets to steady state. Your furnace has to operate for 20 minutes before it gets to the conditions that it was designed to operate in. So really longer cycles than that are more important. So keeping these BTUs per square feet down low makes for a more performing system, even if it's a new furnace. Their best reliable, kind of the unitary box swap world, their best solution sometimes is that we'll put a two-stage system in there. And usually a two-stage system means it's going to run in 60% on low and 100% on high. And there's always this variable period right there. So winds that run on high and winds that run on low. And sometimes low isn't enough and high is way too much. Consider on a 60,000 BTU furnace, low is really 36,000 BTUs. So that helps. A two-stage system will help, but it's not going to give you what you need, because realistically, you could have just went with the smaller of these sizes and been fine. Trying to plug and play heat pumps into an existing application can be disastrous as well. Things that you should keep in mind when you're doing this, when you're looking for a heat pump system or a contractor to install it, looking at that and having somebody say, oh, your ducts are fine, we're just going to slide this thing in here, my guys will be in and out in a day or 8 hours or whatever. You must keep these things in mind. With a heat pump and the heating side, there's a lot fewer BTUs to deliver. So when I had that 60,000 BTU furnace and that 36,000 BTU air conditioner, and the reason we were warm is because we had all that waste heat, and now we're putting in a 36,000 BTU heating source that is going to lose some of that capacity when it gets super cold outside. That's often the experience we hear people kind of complaining about. So there's fewer BTUs to deliver. We need to be cognizant of that. We need to be cognizant of duct sizing as well, because different rooms need different amount of air depending on what their role is in the house. If you have a corner bedroom, it's going to need more air than a side bedroom. So duct sizing is important to get the right amount of air in. Velocity, proper air mixing. If a unit is too powerful, it doesn't run long enough to mix the air, and it's often very noisy. And then you never have time, the cycles are never long enough to actually mix the air in the room. And that's why you can have a house with a two-way vent over by the window, and the unit just ran, the furnace just ran for 10, 15 minutes, and the other side of the room is still cold. Or some other area in the house is still cold because we're not getting proper air mixing. That's the wrong registers, putting the right registers in. And when having the wrong registers with a heat pump, when this heat pump loses some of its effective capacity when it gets colder outside, especially a traditional unitary heat pump, it's going to start blowing cooler air or air that's closer to room temperature. And even a properly installed heat pump, even an inverter heat pump, when it gets really close to the temperature in the room, it's going to slow way down. So the air temperature coming through those vents is going to be much lower. And oftentimes we see the houses we install, once the house has met thermal equilibrium, the air temperature in the register is sometimes just 8 or 9 degrees warmer than room temperature. And that's when you're really in great cruising speed, because it doesn't take much energy to run that system at that rate. But if it was blowing on you, if your room was 75 and you had 85-degree air blowing directly on you, it's going to feel drafty. So having the right registers that keeps the air from blowing on the occupants of the house. You do not want to have air blowing on you. If you need air blowing on you in your house, it's because you have thermal envelope problems. Low temperature air, we talked about it for a second. So the air coming out of a heat pump is much lower than a furnace. We have to be prepared for that. We have to be prepared for that by talking about it with our customers, for one thing, and then we have to be prepared for that as well with keeping the air off of them. And then we have winter performance on a traditional heat pump, like a plug and play heat pump. Winter performance on these units is not good. A typical heat pump runs, the refrigerant coming back to the outdoor unit is 20 degrees usually. That's with a standard single speed system running. When my refrigerant temperature is 20 degrees, it has to pick up heat from the air outside. If the air outside is close to 20 degrees, like 29 degrees, like the Bay Area has gotten several times this year, there's not a lot of heat that can pick up. So it can only pick up 9 degrees of heat as that air travels through the coil. So when it can only pick up 9 degrees of heat, what happens is the cycles end up being very much longer and the air temperature coming out of the vent is really low. And then when the coil exists at that low of a temperature, it's well below freezing. So especially if it's foggy outside or very moist, that thing is going to develop ice on it pretty quickly. And then once it develops ice on it, or frost on it, excuse me, it is going to go into a defrost cycle. And the defrost cycle is basically switching back into cooling. If we switch back into cooling when the house already isn't getting a good amount of heat and the cold air is blowing on the occupants of the house, they're not going to be super happy about that. So keep those things in mind. And then the last one is panel planning. So traditional heat pump systems, there are some other solutions out there, but traditional heat pump systems mostly would be kind of in the plug and play, take the old one out, slap a new one in. It's going to take up more space in your breaker box because a lot of people are going to recommend for that defrost cycle and that low operating temperature problem, they're going to recommend like putting in an auxiliary heating unit. like a toaster element, a really big toaster element that uses a ton of energy. So as soon as it gets cold outside, this toaster element starts coming on to supplement the heating that's not being able to be done naturally through the heat pump cycle. And that uses a lot of energy. So now your heat pump is using way more energy. And those all need to be hooked up to their own separate 220 volt circuit. So you have the heat pump 220 volt circuit, the auxiliary heat 220 volt circuit, and a lot of these units require 220 volts for the air handler itself. And so that's another circuit that needs to go into the panel. So oftentimes there's 6 breaker spaces that need to be utilized in your panel. And putting 6 breaker spaces into your panel and hoping to electrify anything else, that can kibosh your plans to put anything else in without getting a panel upgrade. And panel upgrades are getting harder and harder to get. So proper panel planning can really go by the wayside. And then they don't spend enough time educating customers on all these things we've been talking about. Like if we put a system in your house and it blew cold air on you, it went into defrost mode, the outdoor unit made a lot of noise, my energy bills spike, and I still have cold air blowing on me. Most people would not be happy with that as a comfortable solution to replace their furnace that gave them all kinds of waste heat. They're going to be going, well, at least I had heat. So furnace outputs are much higher than heat pumps. So this is a slide that has ARI ratings on it. This is the American Heating and Refrigeration Institute, and all system combinations that are matched up have this. And this is just to show this is a system that's a 24,000 BTU air conditioner, a 24,000 BTU coil, and in order for this combination to be able to get just a modest 12.5 EER efficiency, they needed to put in an 80,000 BTU 4-ton furnace. So the furnace is twice as large as the air conditioner, and then the heating capacity is 3 times larger than it needs to be here. So this has happened over the years as people bought systems and they tried to get a rebate, like a $300 rebate to hit this number. Contractors, in order to do that with the equipment they sell, they had to put in big furnaces in order to move enough air to get the air conditioner to achieve at these levels. So there's a lot of houses out there that have way too big of furnaces in them for the amount of cooling and heating they need. And most of the time when we see load calculations, unless it's really weird, we see the heating and cooling to be pretty close in requirement around the Bay Area. This is a inverter system, and it's only an 18,000 BTU system. But look at that system has a really high SEER rating, a really high EER rating compared to this here. It provides plenty of heat in this application, and it meets this number or exceeds it. So there are solutions with much less expensive equipment. And I can tell you, if we look at this on a wholesale level, this whole system here costs about what this outdoor unit does. So in order to get all this right, sizing is the most important step when you're electrifying, and installing smaller as possible. We do it all the time. So what we're doing is we're taking the big furnace out and putting the whole system in that's way smaller than just the air conditioner would be previously. So now we're not just matching and taking out a 36,000 BTU air conditioner and 80,000 BTU furnace. We're taking a 36,000 BTU air conditioner and furnace out. We're putting like 24,000 BTUs or 30,000 BTUs because sizing the house is really important. So some of the benefits of doing proper sizing: smaller systems use less energy and cost less to install. Loose houses need more capacity, so they need larger systems. So tightening the house up is super important. Large systems cycle too much in milder weather. Large systems don't run long enough to create comfort or mix the air in the house. And what we found is every room needs a different amount of air. And doing this wrong can lead to a lack of comfort and also really, really high energy cost. So we recommend that you use some sort of an ACA approved manual J load calculation. That's the best. And since we're electrifying homes that are currently running on gas, we're creating a giant amount of energy that's going to be needed in a time that we're not used to delivering. Like in the summertime, we've heard all the time, we got these flex alerts. We need to turn everything off for a period of time so the power doesn't go out. And now that's going to be happening in the heating side too if we do this wrong. So the more efficient heat pump systems that we install, the less we have to worry about all that because there's less drag on the system. So doing a properly sized system provides load. The Manual J provides loads and airflows for each room, resulting in better comfort. It considers your local weather, the house orientation, and the occupants in the house. Considers different construction methods in each room. So sometimes we'll see a house that has a flat roof and a slab floor was maybe added to the house. We can actually take that into consideration in that load calculation. It also takes into consideration things like the windows, the roofs, the floors, the walls, how much insulation is in there, what direction the house is facing, and the local weather data. And then these are available in multiple iterations. We happen to use RightSoft because we're just used to it, but there's also a new one out there called Quick Model, and there's several other load calculation programs that are based on Manual J. But if you're a homeowner and the contractor comes in and does one on paper, there's no way they can do a proper load calculation on paper that takes in room-to-room conditions. Why BTU and kilowatt is not a reliable sizing method. Basing heat pump size on peak gas is a way to verify. It doesn't consider homeowners' habits and their efforts to save energy, does not provide room-by-room load requirements. It doesn't consider multi-room options like mini splits, and it won't uncover problems with the existing furnaces. So peak gas is a process where we look at how much gas they used in a certain day or month in accordance to what the temperature of the air was, and then we do a calculation based on how much energy the gas holds, and we come up with the capacity of our system. And the problem with that process is that it doesn't consider homeowners' habits. And so we run into people all the time that either have 2 floor furnaces in their house and only one works, or they're only using one because they're being conservative, or they're not running the furnace because it costs too much to operate. So if we try to use the peak load gas to design their system, the numbers are going to be off. So we can't go by somebody's not using their furnace to design the heat pump capacity of the system. We're going to get it wrong every time. So now we use peak load gas to verify the system sizing. And so once we do our load calculation, in some cases, we'll look at the gas rate and kind of make sure that we're in the right ballpark. We have a big opportunity and there's a big risk coming if this isn't done right. 90% of the houses in California rely on gas for space or water heat. 12 million California homes that need to be upgraded that use 90%, California homes, 99% with gas or electric resistance water heaters. So 99% of those 12 million homes are opportunities that are ripe for a heat pump water heater. Getting rid of an electric resistance water heater is going to save you 4 times on your energy costs with the electric side. And replacing a gas water heater with a heat pump water heater is always going to be safer and more efficient as long as that house isn't already in Tier 4 energy. And 93% of single family houses have gas as the domestic hot water. 11.7 million houses, 85% of those single family homes use gas for heating. And 3.4 million houses in California have no air conditioning. So as we go in and we retrofit out these furnaces and we put in new heat pump systems, and we put in the wrong solution of a heat pump, one that uses a lot of energy to start and a lot of energy to run, and we have a big heat wave like we had last year in October where it got to be extremely hot everywhere. When we turn on 3.4 million new air conditioners, do you think that that's going to be a good thing or a bad thing when it comes to existing grid capacity? So they are working on existing grid capacity, which is good. But this is a really good opportunity for us to make a marked improvement in the predictions by putting in really efficient systems and just doing a little work to the house at the same time. This is what a load calculation should look like. And if somebody's doing a load calculation, like drawing a thing on a piece of paper, and they're going to come back to their office and do one of these, you should ask them for this so that they can see it. These things show what's really going on. Once again, this is a 1,500 square foot house in Fairfield, California. And if anybody's ever driven up Highway 80 going to Sacramento in the summer, it's hot in Fairfield. And it, got down as low as 29 degrees there this year as well. This is a 1,500 square foot house that was built in the 50s. And we took out a 60,000 BTU furnace and a 3-ton air conditioner. That system was very old. The ductwork was really bad. And we were able to put in a system that was 1/3 the size. We ended up putting an 18,000 BTU system in this house that will more than take care of any criteria for the heat side and more than enough for the air conditioning side. We were even surprised with this system, how low of cooling capacity it needed. This house was upfitted with new dual pane low E windows. And then we insulated the attic space really tightly. This system was also in the closet here, and some of the ductwork was actually inside the building envelope. And one duct had to kind of go up into the attic to get over to these rooms. But if we didn't know this, if we didn't measure all this and know, every other contractor would have just put another 3-ton unit in there with another 60,000 BTU furnace. And we would have missed all that opportunity, energy savings, and comfort. And they would have put in a system that probably cost twice as much on the wholesale level as the one we ended up installing. So we were able to pass the cost savings along to the customer. But let's take a little bit of a closer look at this. So these 2 bedrooms here, spare bedroom 1 and spare bedroom 2, this couple bought this house before they had their first kid. So now at least one of these rooms I know of has a baby in it. But both these rooms are 9 foot by 10 foot, 90 square feet, but they need different amounts of air. Remember, we talked about CFM as 1 cubic feet per minute of air is about 1 basketball of air every minute. So this one needs 31 basketballs of air every minute. This one needs 48 basketballs of air every minute. And we do another training program where we train contractors and we ask them, why do you think this is? And a lot of people can't answer this question, but this is why doing a load calculation is so important, because most people look at this and they go, 2 rooms the same size, 2 ducts the same size, we'll call it a day. But what's going on here is we have Mother Nature existing on 2 outside walls here. So the driving forces from nature are working here and here. So this room needs more air to condition. If this hadn't been spotted in the load calc, if I would have installed this unit 15 years ago, I would have put another 3-ton, 60,000 BTU system in before I understood building science and did load calculations. But now we know. So if we put the same amount of air in both these rooms, what's going to happen is one room is either going to over condition or one room is going to under condition. With the right amount of airflow in each room and the right size duct in each room, and usually it's the same size duct, we just put a damper in here, a little valve in here, and slow down the airflow. But by doing that, we can really balance the air off in here and keep the house very comfortable. But this is how we get high room to room comfort. Okay, swapping like for like sizing. So an existing 1,500 square foot house with a 3-ton system, 60,000 BTU furnace. The new one now is a 36,000 BTU heat pump. We have 40% less heating capacity. That traditional heat pump loses capacity when it drops below 40 degrees, and the house may not have enough heat when temperatures drop below 40 degrees outside. So what we have is we have a house that has a much smaller heater that now is not going to work as good when it gets cold outside. So what happens there is we're delivering less heat as Mother Nature is pushing on the house. If we don't have a really tight envelope, the house is going to get cold and the unit is not going to be able to warm it back up again. And that's why you'll hear people talk about we need a heating element in there to heat the air up, because the appliance I sold you can't do a good enough job. But just by doing a few things like air sealing a bit, insulating the attic space, burying the ductwork in the attic, and putting in the right system that has good low temperature operation capacity can take care of all of these. But buying the wrong one can leave you very uncomfortable. And I would say if I lived in that house and that situation happened, I'd be a little upset. Emergency replacement of a heat pump is ripe for poor results. So now we're seeing this going on. Service and maintenance technicians come out, you got an old furnace, 20 years old, maybe there's a problem with it. Maybe it's like, hey, there's a part broken, I can't get the part for a month, but I can install a new system for you tomorrow. and they're going to open up the catalog and they're saying, hey, this is the right size. This is the same size as your air conditioner. We'll put this in. We'll be all good. Realistically, most HVAC systems, this is a fact. Most HVAC systems are sold by maintenance and service technicians, not by designers. Most HVAC technicians are only experienced with gas furnaces. We've been heating in California. What was the slide before? 96% of all the houses in California have had gas heat for years and years and years and years. So HVAC companies are really, really good at working on heating systems that are gas. But there's going to be a learning curve before they're really, really good at installing heat pumps and understanding the difference, right? So they look at their 3-ton system, put a new 3-ton system in there, and all the problems on the last slide happen. Techs and maintenance people are really up to speed on the best design and technology because they're service technicians. They're out there fixing things. I don't have a problem with service technicians at all. I have been one my entire career. And I am personally guilty of taking out systems and putting the exact same one back in, and finding that on a maintenance visit and talking the customer into a new system at the time that the maintenance was done. I would say if you're thinking about upgrading to a heat pump, don't fall into this trap. If somebody recommends this system, ask for a designer to come to the house, ask for a load calculation, ask about your ductwork, because I'll tell you, back in the day when I was in my early years, 15, 20 years ago, I was a selling service technician. We were taught by the company we operated with not to worry about the ductwork. Don't worry about the ducts, they're always gonna be fine. I didn't know any better until I became a building science guy. So unfortunately, a lot of technicians are just kind of looking for a quick, easy sale, and so is the company. So there's no time for them to perform the meaningful calculations. And then customers often end up with really energy guzzling systems that put a bad taste in their mouth, and then they tell all their neighbors, why would you get a heat pump? They stink. So results of poor planning: rush to get back online and unexpected expense drives rash decisions with people. Like if your furnace is working and you call a maintenance tech out and they say, we found a problem and now it's not going to work anymore, or your furnace is broken and you call out a service technician and say, we don't have your part. This puts people in an interesting situation, right? Because they're going to go, I don't have heat. I need to make a decision right now because I need to keep my family safe and warm. And they often buy a system under duress conditions that if you wouldn't have bought, if you would have known all the inside information about it. So my recommendation is always wait on that. Get a designer to come out to the house and take a peek at it. Get that repair done. If it costs you $500 to get the repair done, to get the unit back online, and they're going, hey, well, you should replace this because it's $500. Get the repair done, because if you get the wrong system put in, $500 is going to get sucked up in 3 or 4 months of high electric bills. Unplanned replacement often becomes a low bidder option too. This is another thing that happens, is when it's broken, we didn't plan for the investment, then we just start looking for the cheapest option possible, and we start bringing all these guys in, and it becomes a race to the bottom. So if you're going to get a heat pump on, you don't want to fall into that. HVAC professionals with no experience or knowledge of envelope performance can be a problem. You want to call the companies you're dealing with and ask them if they do attic insulation and what type of survey of the duct system are they going to do. It often results in larger loads and unnecessarily panel upgrades, expensive to operate systems. We talked about that. How far should we go? Ooh, time check. Oh, okay. It doesn't have to be complicated, just a handful of things that need to be done a little bit better. We talk about this all the time. There's no silver bullet to making your system better, but there's 100 silver BBs. So we just do a lot of little things better, and it gives you a much better system. The contractors take pride in your work. We can all do this better. Do a load count, pay attention to the distribution system, the ductwork, seal the major leakage penetrations, insulate the attic space, and put in a really good inverter system. It's cheaper to train your crew to do work and testing, and then they have to fix it while they're out there. They learn what it takes to fix it. It's cheaper than sending the HERS-rater guy out there and then him figuring out something failed and then you send a different crew out to fix it. This was a hard lesson I had to learn in my own company. So when installers test their own work, they learn from the test results. Home performance monitoring is expensive, but tracking the home performance by analyzing utility bills are cheap and easy. So just look at your bills. Are you saving money? This is a family in the Bay Area that we did a job on. This is just a little case study, and we're nearing the end here. But we took out an old system, and this was a really old house. This house was had to be 90 years old. This is our load calculation. Unexpected high cooling load in this house in Berkeley. It was really unexpected, but they had a bunch of single pane windows on the south and west. But if we would have just done rule of thumb on this, we would, well, first of all, we would have put a bigger system in than we did. So the found conditions, we found a 92% 80,000 BTU furnace. That gives us 74,000 BTUs of delivered efficiency. The attic was really bad with air leaks and bad insulation. Fixing the attic took 12 man hours. It was myself and my 16-year-old son. And I worked for 8 hours. He went out and started cleaning up at about 4 hours. And we replaced the water heater on this as well. There's my son up there with junior air sealer with his foam gun, getting after those air leaks. But if you look at the left here, this picture, we could actually see down inside the house. This was a really old house with a set of pocket doors that when we looked from upstairs, we could see down into the house. This is a massive leaky house. They could never really get the house warm and comfortable with the big old furnace they had. So instead of like putting another big system in or just going for it without looking in the attic, we actually did the air sealing. We sealed up all the gaps, we sealed up the coffered ceilings, and then we put a beautiful R50 insulation in there. So now the attic has to be 50 degrees warmer or cooler for any heat to transmit through the space, and there's no more air leakage. We reduced the air leakage on this house by 60%. It was testing at almost 3 CFM 50 per square foot, and we got it down to 1.5 on a 100-year-old house. This is the equipment we installed. New Bradford White heat pump water heater. Beautiful new Mitsubishi system. 65-gallon water heater. We went from 50 to 65 because the thermal storage battery effect of a heat pump water heater is beneficial to the grid. We designed and installed the system with the load calcs air sealing. We put a 36,000 BTU system in there, and we modified the existing. The ductwork was newer. Their old system wasn't that old. We modified that and sealed it up pretty good. And this was what our customer had to say. This is, if we look at the underwork, the system works great and much cheaper to run. Also much quieter than our previous gas furnace, and the extra installation that was added has been a major improvement. Even without the heat pump, our upstairs rooms are much more stable in terms of temperature in both summer and winter. So that concludes my slides for why home performance is important with electrification. And now we can take some questions.